Thanks everyone for joining this week. Another installment of the IGS Global Seminar Series. This week we have Luke Zoet from the University of Madison, Wisconsin. Luke is going to be presenting on how glacial slip varies across different bed conditions. So we'll pass it over to Luke. And just like usual, I'd like everyone to hold their questions until the end or drop them in the chat, and then I can read them off there. Reminder that this seminar is recorded and will be posted to the IGS YouTube channel by the end of the week. So yeah, with that, I'll pass it over to Luke.
Great. Thanks, David. You get this here. Okay.
Good.
Okay. So yeah, like David said, I'm going to talk about work that we've been doing sort of at Wisconsin/Iowa State for maybe the last 5 to 10 years, where we've been looking at a range of different mechanisms of slip. And when I say examining it across different bed conditions, you can think of a lot of times when people try to categorize the subglacial realm, they'll do it into one of two categories: hard versus soft. Hard meaning it could be like a crystalline bedrock that doesn't deform, and soft being a granular material that does deform. And so we'll look at how slip varies across those different parameter spaces from a combination of like experiments and modeling within a tiny bit of field work that we've done. So this is not obviously work that's done in a vacuum, so it's done with a whole host of collaborators. Some of you are on the call I see here, so there's aspects of it that you can answer better than I. But I'll sort of try to sum it all up in this talk today. Um, so when just to start it off and get everyone on the same page, when you see a map like this of Antarctica, and this one in particular is color coded by the surface velocity. And this is how fast you can observe things going essentially from space. And you'll see that certain areas like over here in the Cycle Coast and Thwaites are moving really fast. And notice this is not a linear scale, it's a logarithmic scale. And when we look at these areas that are moving really fast, what we find is that there's different components that are contributing to the motion. One is obviously internal deformation of the ice, but another is focused at the ice bed interface, and it's a process, a lot of times termed sliding, sometimes termed slip, right? And it's occurring right near the ice bed interface. And so one of the first treatments of this was looking at basal slip, was from Nye. And in this diagram here that I like from his paper, this is the surface of the glacier. This would be the bed. This is if you're looking at the glacier from the side. And if you were to drill a borehole through the glacier and then come back some time later, you would see it's deflected, right? And what Nye reasonably postulated that was that a lot of this motion that you see at the surface isn't necessarily coming from purely deformation of the ice, but is instead come from slip at the bed. And an analogy I would give is this is sort of like putting an ice cube on a board and slightly tipping the board. And right where the ice cube meets the board, and there's sort of friction there at the ice bed interface, that process of friction is what's regulating how fast that ice cube can slip down the board. And in a lot of instances, fast-moving glaciers have a big component of their forward motion coming from this sliding or slip process that's occurring at the bed. One thing that at the time folks didn't realize, or it wasn't in the glaciological literature at least, was that sometimes the bed of the glacier isn't necessarily always made up of a hard, non-deformable rock. In a lot of instances, like here in the upper Midwest in Wisconsin, the bed is actually made up of a granular material that can itself deform. And so you have not only sliding atop the bed, but also deformation of the bed. And so when I say slip, that's what I mean is a combination of sliding and deformation occurring at the bed. And we know from studies like this one from Matsumoto, where people have looked through the ice in a place like Antarctica and mapped the bed, that the bed is composed of both hard and soft. And so this is an active seismic survey, and you can see this sort of break right here that I'm tracing. That's the bed of the glacier. And they've used different techniques here to categorize the bed as either hard, that's sort of shown up here with these black dots. So the places associated with that are hard, and other places that are soft associated with sort of these gray bars here. And so the bed of a glacier can be, in some instances, exclusively hard, in some other instances, exclusively soft, and in many instances, sort of a combination of hard and soft slip. So we kind of like to know how the glacier slides over these different bed composition specifically. When we try to parameterize or make postulations about how that slip is occurring, often what we are using is or trying to create is something called a slip law. And so this is an example of one of these, or this is a definition of it, is the slip law relates the driving or shear stress, which are often assumed to be balancing each other, which is probably not the case in many instances, but it's an assumption we make, to the sliding speed. So we want to know either you can think of it as the glacier moves faster and faster, how much harder is the bed able to push back? Or conversely, as the driving stress goes up, how much faster will the glacier go? And so it's a pretty simple thing, but it's pretty fundamental in trying to prescribe how glaciers move over their bed in time. And getting this right is pretty important for getting accurate predictions into the future in particular. And so there's been a range of these slip laws proposed. There's a lot of ones that are just these sort of power laws that as the sliding velocity goes up or the slip velocity goes up, the basal friction or basal resistance increases with it in a sort of unbounded way. And so these are what's in a lot of ice sheet models. A lot of times they're termed like Weirton sliding laws. Another possibility is a Coulomb material. That's one where as you push on it, nothing happens. You push on it, nothing happens. You push on it harder, the bed breaks. After that, the bed only provides a finite amount of resistance that no longer is dependent on the actual slip velocity. Some of these other more process-based ones take into account how cavities are formed at the beds of glaciers, and they can give what's sometimes called a double-valued sliding law, where the resistance reaches a peak and then decays down as basically cavities at the ice bed interface get so expansive that they concentrate the stress in a small area, in theory, that can't resist it. And then there's a regularized Coulomb mechanism here where the resistance increases as the sliding speed increases, but approaching some sort of bound, right? And in this case, we'll call it the Coulomb bound, so that's why it's called regularized Coulomb. And so all these have been proposed. Many of these have been used in models, and what we kind of want to figure out is, does this hold? And does it hold for different bed types? Does it hold for hard or soft or other types of conditions as well? And so it can make a big difference, right? So in this paper by Catherine Ritz, what she did was look at a number of these different slip laws and make predictions about the sea level equivalent ice that would be dumped into the ocean near the Amundsen Sea embayment glaciers over different basically conditions in their model. And what they've done here, the different colors that you see, is they've changed the slip law that they've used. And so in this, you can get something like a 50-fold difference in the amount of ice that's discharged in the ocean by essentially just choosing the different slip law, right? And so it makes these flow models and their prognostic ramifications highly dependent on essentially what your choice is for the form of this function. So the objective here is to determine the appropriate slip law or laws for glacier motion for different types of bed conditions over time. And so this talk is going to be focused on how we do it a lot of the times at Wisconsin and other collaborating institutes that are listed there. And it's a combination of experiments in field and experiments and theory development, essentially. And the reason we do that do it this way is because it's really hard to figure this out in the field. It's really hard to figure out what the slip law is just from looking at the field data. One reason is you can't easily isolate the independent and the dependent variables with remote observations. You're just subject to whatever nature gives you. And so in that way, you can't really probe the system the same way you would, for example, in a model, right? Another way that people sometimes try to interrogate the bed and look at the stress conditions there, for example, is to drill to it. But that can be complex because by drilling the hole to the bed, you sometimes disturb things like the subglacial hydrology and other aspects of the basal slip that can make it challenging to separate what you did from what nature would have done in the situation without you being there. So our solution is to go to the lab. We use devices like this. And so this is a ring shear device. This is the one at UW-Madison that we've built over the past 5 years or so. And what this is it is housed in a giant walk-in freezer. And this part right here is the sample chamber. And this one, the sample chamber is transparent. And you take a disc of ice and you place it atop some bed material. So in this case, the bed material is till, right? A soft till. But you can put hard beds in there. You can put whatever you want. And then the top of the ice ring is gripped by a set of platens that spins the ice ring over the bed at a prescribed rate. And this big thing you see up here is a gearbox that's got a 2 million to 1 gear reduction ratio that allows us to generate the massive torques we need to maintain a constant sliding speed on the system. And when we do that, we measure the resistance the bed provides to sliding at these different speeds. And then we'll increase the speed and do it again, increase the speed and do it again, or increase the pressure and do it again. And we can systematically step through changes in basically pressure, confining pressure, how we're holding the system together, or sliding speeds. And we can't even drive the thing in a stress controlled mode. And you can see there's all sorts of cables and wires coming out of this thing. We measure a lot of different properties, things like the water pressure, the temperature at many different points. We have these cameras that can look through the sample chamber into the ice and monitor it. This whole sample chamber is actually sitting inside of a big tub of antifreeze right here, and that antifreeze helps us regulate the ice temperature to within 1/100th of a degree. And so when we spin this thing, we're at the right pressures, we're at the right sliding speeds, we're at the right temperatures. We have proper till in there for the case of till beds, but the downside is the experiments take a long time, right? So to not scale things necessarily, or to run things in the natural conditions, means that the experiments take, 4 to 6 weeks a lot of the time. Here's just a sort of another blow up of it. So this is kind of a cartoon of what's inside of this sample chamber here. So here's this upper platen, like I was saying, that's grabbing the ring. And in this case, it's on top of a till bed, and the ice is being spun, and the till bed is water saturated. Water is allowed to leave the till space or enter the till space as the till dilates and contracts. And we can sort of monitor how that's working in addition to the stresses that we're also monitoring as well. And so, okay, so the basis for the talk is to try to look at these 4 different end members, right? And how you might expect this slip law to behave in these different end member cases. One is basically clean ice sliding atop till, right? So no debris in the ice, and we have an underlying till layer that can deform if the system is able to deform it. Another is a similar type of situation, but the base is made up of bedrock. So in this case, the bed material will not be able to yield, right? The ice has to yield to the bed and whatever topography it has. A third case is, again, a till bed, but where we have debris in the basal ice. And the fourth case is a bedrock, or a bed made up of a rigid bed, but we have debris, and we have debris in the ice in this case. So first, we'll talk about these debris-free cases, in this case, this one. And so what I'll do is I'll put these little cartoons up in here so you can keep track of which one of the 4 end members I'm talking about. So when I talk about soft beds, you could think of something like this. So this is Muleyoko Glacier in Iceland. You can see the glacier up here in the upper left. And this big pile of gray stuff is dirt, right? And in just a few years before I took this picture, the ice was overriding this area. And it was moving stuff around. It was digging out these holes where these lakes are. It was piling up stuff in these hills that's making drumlins. And so there's a lot of bed deformation going on in this case, as evidence from sort of the glacial geomorphology that's left behind after the fact. Now, when the ice slides over a till bed, these are 2 potential slip laws. And so also a lot of plots like this where sliding speed is on the x-axis, increasing from left to right, and shear stress is on the y-axis. Sometimes I'll normalize the shear stress and call it friction, but it's effectively the same thing for what we're talking about here. So one end member case could be like a coolant material where you push on the bed, nothing happens. You push on the bed, nothing happens. You push on the bed, nothing happens. You push on it, you reach the yield strength of the till, and then it begins to deform, but with no longer a dependence of the rate at which it's deforming on the applied stress. Conversely, you could have a bed that continues to push back harder and harder and harder, sort of like those Weirtman or viscous sliding laws that were proposed earlier. And so we want to determine which one of these is right, or either one of them right. And so again, this would be like the ice essentially sliding over the till without the till deforming. And in this case, all of the motion of the glacier, or most of the motion of the glacier, and most of the slip would be facilitated simply by deformation of the till, and there would be minimal amounts of sliding at the top. And so when we do this, when we put it in the ring shear, we find something like this. So on the x-axis is the sliding speed, and on the y-axis is that drag. And this dashed line is that Coulomb strength of the till. This is how strong just the sediment is that's in the bed if you were to, for example, take it out of the ring shear and test it in a different setup, like a direct shear apparatus. What we can see is there's two experiments here, and in both cases, as the sliding speed goes up, the resistance rises until it reaches the Coulomb strength of the till, and then it sort of rides along the Coulomb strength of the till. The reason that there's two experiments here is one had big clasts in it, so big rocks that we put in the sample chamber. That's the red one here. And the blue one had no big rocks. It was just sort of the regular granular fractal till up into some cutoff point. But in both cases, the stress increases until you reach this Coulomb strength, at which point it sort of plateaus past that point. And so when you go back to this idea of which one of these is it, well, it's sort of both or neither, right? It has this viscous component as the ice moves faster and faster and exerts more and more traction on the bed. Eventually, it exerts enough traction on the bed where it meets the yield strength of the till. And then what was happening with the ice sliding over the bed no longer becomes sort of the weakest link in the chain, and the weakest link in the chain becomes the actual till itself deforming. So you can this transition where it goes from the viscous strengthening to the Coulomb depends on what the bed is made up of. It depends on if there's big class in there or not. So when we have big class, that transition happens at a slower speed. And when they're smaller and no class, it's the same general function, but that transition from the one type of sliding to the other happens at a slightly higher speed. And that transition speed is we call it U sub t. And so you can think of it as before this point, the ice is largely sliding atop the till without a lot of deformation going on within the till itself. Whereas once it surpasses this point, you've put enough traction on the bed where the till deforms, but you're also getting sliding up over the top. What's regulating this and sort of a fundamental level has to do with what's actually at the ice bed interface. So in this case, imagine this black line here is the interface. This would be the ice, and this would be the sediment. And if you have these clasts or rocks at the ice bed interface, as the ice is sliding from left to right, it's loading a bunch of stress on the upstream side of this clast. And eventually, as the ice goes faster and faster, more and more stress is applied to the upstream side of this clast. And at some point, it overcomes the resisting stress down here that's supplied by the bed, and that clast will mobilize. And once that class starts to mobilize, that's when that transition speed is surpassed. And so we have a way to sort of estimate when that transition speed would occur from sort of knowing various engineering properties of the sediment and various, fluid essentially properties, the viscosity and whatnot of the ice as to how the stress is applied on the upstream side. And you can imagine in this case, this ice is debris free as it moves around here. And so it can regulate around this, or if these things are big enough, it will viscously deform around them. And so here's sort of a cartoon of it, of this process. So here's the ice bed interface, and here's the stationary class because at slow sliding speeds, there's not enough stress basically on the upstream side of the class to cause it to plow through the bed. That's what we call it when the class moves through the bed. And then as the ice moves faster and faster, there does become enough stress on the upstream side, and the class becomes mobile, and you get into this sort of Coulomb regime essentially. Okay, so a way to simply express this is with something called a regularized Coulomb expression, which is what's up here. The basal drag is related to the effective stress. So this is the weight of the glacier minus, or the overburden stress of the glacier minus the water pressure. Tan phi is simply the friction angle of the sediment. U sub b is the sliding speed, and this is that transition speed. And 1 over p is an experimental factor that deals with the rollover. So something like this captures both the rate strengthening component here, gives rise to this rate strengthening component, but also is partially limited by this Coulomb strength of the till right here. Hence the name regularized Coulomb. And so when we use that simple model, like I showed in or parameterization of that press slide to predict what we would get from the experiments, it does a pretty good job, right? So this is one model compared to the experiment points without class, and this is another version of it compared to the experiments with class. And so when we look at the general response of debris-free ice sliding over a till bed or deformable bed, what we find is something that looks like a regularized cooling response, right? And we can explain the mechanics that are going on, and we can give you a way to parameterize it that doesn't have any tuning variables. Like, for example, if you gave us some till, we could tell you what all of those parameters are. There's not really any tuning per se in this available. Now, what happens when we talk about a bed that just won't yield, right? Like a bedrock bed, right? Something that's made up of rock. And so there's no chance that the ice is, or there's little chance that the ice is going to exert enough traction on it to cause it to deform or fracture or anything like that. And so you can think of a bed like this. So this is from Switzerland. This was right under the glacier a couple of years before I took this photo. This is a big obstacle. The ice would have had to flow from right to left and move around this material as it did that. And so what happens is imagine you have a bed and then you have some obstacle at the bed. The overriding ice has to move past this obstacle. And however fast it can get around this obstacle dictates how fast the ice above it goes. So if the ice has a hard time getting around this obstacle or does it very slowly, the overriding ice is going to move very slowly. If it can get around it really quickly, then the overriding ice is going to move particularly quickly. So it's all about how fast ice gets around these obstacles at the bed and how these obstacles provide some sort of resistive stress to holding the glacier back. So the speed of the overriding ice is limited by how fast the base can get around an obstacle. And so in a lot of instances, people have tried to look at this problem in a simplified case with a sinusoidal bed. So this would be looking at the glacier from the side, just at a small part of the bed. And imagine this black here is bedrock and the white is ice, and the ice is flowing from left to right. And what happens is in the lee of obstacles at the bed, the ice is moving fast enough. It can generate opening, which is called a cavity, right? And as the ice moves faster or the water pressure goes up, that cavity will get bigger and bigger. And so think of the roof of the cavity becoming these progressively bigger dotted lines. But what that's effectively doing is concentrating the resistive stress, the thing that's holding the glacier back, to just this portion of the bed, the area where the ice is still in contact with the bed. And as the cavity gets bigger, that portion gets smaller and smaller, and the resistive portion in the slope of the area that's actually pushing back changes too in this sort of sinusoidal case. And so this gives rise to different cavity sizes as the speed goes up, and that concentration of the stress in smaller and smaller areas as the cavity gets bigger produces an interesting drag response. So again, on the x-axis here is sliding speed, and this dashed line is, or the solid line is the resistance that we measured. And what you see is the resistance first goes up, hits some maximum, and then decays. And the reason it decays is because once the cavity gets big enough that it surpasses this inflection point, the resistance it can provide diminishes, right? And this is a so-called double-valued sliding law. Andrew Fowler, Laboucherie, a lot of other folks had worked on this, and they were right? That is the right mechanism for how ice slides around obstacles like this, because those cavities are so important. The thing you might ask yourself, though, is how can we extrapolate this to the field, right? This is a really idealized bed configuration that's a sinusoid. And if you've been out to glaciers, the beds don't always look like perfectly periodic sinusoids, right? And so what we've done is try to extend that work to beds that have the real topography. So we went out to a bunch of glaciers in Switzerland and Canada and built real high resolution digital elevation models of the beds. And then we used Elmer ice to slide the ice over these beds. And what we did this for was a little bit different than you would normally build an ice flow model to do. We weren't trying to impose a slip law when we did this. What we were trying to do was use this physics that we knew was important and then apply it to beds that had real shapes, and then add up all the points of resistance as we basically make the ice slide over it faster and faster, and look at how that slip law what slip law would come out of this. So we're basically using the modeling to determine the slip law, not using the slip law to impose the modeling, right? It's sort of the opposite way that this is done a lot of the times. And so, for example, if we look at one of these glaciers, like this Sopheren, and this is the forefield, or the area that was right in front of the glacier that was under the glacier just a few years before the study. What we find is as the sliding speed of the ice being forced over that irregular bed increases, those cavities get bigger and bigger and bigger, like you might expect. So this upper panel is the ice sliding at 10 meters a year. And everywhere there's this beige color, the ice is in contact with the bed. And so those are the areas that are actually providing resistance. They're pushing back on the glacier. Whereas everywhere there's these blue color, there's a cavity. And so in those areas, the ice is not in contact with the bed and can't push back. And as the ice goes faster, 10, 20, 50, 100 meters a year, you can see that the blue area gets bigger and bigger and bigger, meaning the parts of the bed that actually are supporting the drag, supporting the resistance, are getting smaller and smaller and smaller. And so when we add up all the resistance that we get from these parts that are left over and not under the cavities, we can begin to sort of determine what the response is, what the drag response is, what the slip law is. And so for these um, four different glaciers I showed before, we got sort of a surprising result. All of them show the same general pattern. So on the x-axis here again is slip speed. It's normalized here by a couple of things. And the y-axis is drag normalized by the effective stress, so you can think of it as drag. What we find is that as the glacier moves faster and faster, the resistance of the bed provides goes up. But unlike an unbounded power law, it rolls over, right? And this is real glacier beds. It has all the real sort of complicated mechanics in it, and it goes flat. And we see that for all of these beds, right? They all sort of go up and roll over. And that said, that was interesting, right? It suggested that, again, this regularized Coulomb form, which is this dashed blue line in all of these plots that can be fit with this type of expression, seems to apply also to hard-bedded glaciers because of these processes of cavities and essentially because of the irregular distribution of bumps on the bed that are shifting where those cavities are focusing their resistance at. So when we look at this one, clean ice sliding atop the hard bed, we also get a regularized Coulomb. Okay, that's interesting. Maybe it means that there's sort of one friction law, one slip law that we can apply for a multitude of beds and make this easier, right? So it seems as though the regularized Coulomb could be used as a universal slip law. However, there's one potentially important process that's been omitted in everything I've shown so far. And that's when you go back to this diagram by Nye, and he showed, slip at the bed. What he omitted, and whatever most people omit, is the fact that the bed of the glacier, that basal ice, has lots of debris in it. Right? It's got lots of sediment that it's entrained, and that sediment is dragging along the bottom, right? And so this is a picture from Engebring. This is a subglacial lab in Norway. And what you see here is all this debris-rich basal ice sliding over the bedrock of the glacier. So this is a point where you can actually access the bottom of the glacier. And so it's not this beautiful, clean, perfectly viscous material that's sliding over the bedrock. It's this sort of nasty mashup of material that has all sorts of bits and rocks in it that it's dragging along the bed too, which are an additional source of drag that, we've sort of omitted, right? So here's a picture. These are big clasts in there that may be the size of your fist that are embedded in the bed. So basal ice commonly has lots of sediment in it. And this isn't limited to just Ingerbring. So this is the front of Thwaites. This is the ice fin robot that they drove under there. And you can see all the sediment that's in the basal ice. This is a core from Pope Glacier next to Thwaites that's got it. This is Willens with side-looking camera that was dropped on a borehole they drilled. In almost all instances, there's basal debris in the ice, right? It's pretty ubiquitous. So the omission of it could be problematic if it turns out to be important for its contributions to the drag. And so if you think of a diagram like this, well, here's the ice and here's the particles. Those particles are being pressed into the bed. And as the ice is being dragged along, they're having to be pulled along against the bed and they're scraping it up and providing extra source of resistance. So here's a striation from a glacier, and this is just proof that, this is a source of drag that is, important. It's shaping the landscape, right? When we look at something like this is all smooth and has these striations on it from those types of processes. But a big part of the reason why the glacier has this shape is because a big or some portion of the energy balance of the glacier, especially the sliding energy balance, has gone into sliding those rocks over this bed and shaping the terrain. So what's happening, right? This is a lot of work from Colin Meyer and Alan Rempel. They've put a lot of work into understanding this frozen fringe process. And what that is it's the ability for ice to start to penetrate down into the underlying sediment and entrain it in the basal ice. And what it does is there's some sort of curvature here that affects the surface energy balance. And if the pressure of the ice minus the pressure of the water is overcome some pressure, some infiltration barrier, the ice will start to work its way into this system, and you'll start to get ice saturation in this pore volume. And it's very high. The ice saturation is very high up near the up high in the ice column, and it decays with depth. And so when people have tried to look at the role of this debris, here's a study from Ingebrigtsen where they put this panel underneath the glacier. So you walk up this tunnel right here, you go up this vertical elevator shaft thing here. You can jam an instrument right at the bottom of the glacier. And that's what this panel is here. So I'm at the bottom of the glacier looking down at this panel. And as the ice slides over this thing, the debris that's in the ice drags along this panel. And this panel is specially outfitted to measure the resistance that drag supplied. And so in this paper by Neil Iverson and others at Engelbreen, they found something that was very interesting and potentially concerning, which is that when they actually measured the drag, they found that like 50% of the overall drag that the glacier bed was supplying was actually coming from this debris, which would mean that when we omit it, we're potentially getting 50% of the problem wrong, right? And we know that the debris is pretty ubiquitous, so it could be important. And this isn't for super high debris concentrations. It's only like 2 to 11% in this case. And so what happens when we put debris in the ice and slide it over till? So this is a project that we did where we grew this quote unquote frozen fringe, which is the mechanism by which debris gets into the ice. How we did it was we used the ring shear and we let it just sit there for about 4 to 6 weeks without spinning it. And that caused this frozen fringe layer to develop. So here's debris, free ice. Here's debris, heavily debris laden ice. And this is, in this case, glass beads or sediment that's water saturated underneath. And then we started spinning it, and we saw how this frozen fringe, as it moved and deformed and interacted with both the debris-free ice and the unfrozen sediment below, how does that affect that frictional resistance? How does it affect the slip? So here's a video through the system. And so this is sped up like 3,000 fold, but you can see the ice is moving from left to right. This is looking through the walls of the ring shear. In this case, this is till. Here's this till at the bottom. It's being frozen into the bed, and you can see there's some deformation that's occurring at the bottom. When we take the ice ring out, we have this layer of frozen till or frozen fringe that's incorporated into the basal ice over time. Here's another example of it. This is the glass beads. The ice is moving from left to right. This frozen fringe right here is perfectly mated to the ice and moving at the same speed. And then you kind of have this layer where there's a bunch of complexity below it. All this interesting stuff that's happening inside of this zone. Now, here's the results, right? This is the main result I'll show for this part of it. And again, it's one of these plots where the sliding speed is on the x-axis and the frictional resistance is on the y-axis. And what we found was, again, something that where the frictional resistance increases as the sliding speed goes up until it reaches this Coulomb bound, at which point it sort of rides along the Coulomb bound. If you had asked me before we ran this experiment if this is what we would find, I would have, this is not what I would hypothesize. I would hypothesize you put a bunch of debris in the ice and you slide it over this granular bed. It's probably going to just behave like a Coulomb material all the time, but it didn't. We still had this sort of rate strengthening component before we got into the truly Coulomb regime. Now, once we were in this regime, once we were living in this space, for example, we tested it a little further. And so this plot is effective stress. You can think of it as how much we're compressing the system versus the measured shear stress, how much resistance the bed is providing. And what we find is as we compress the system harder and harder and harder, the resistance to shear goes up linearly, which is a hallmark sign of that the bed is behaving like a Coulomb material. So we're pretty convinced that once you're in this area, it's largely a Coulomb response that's dominating. It's largely this sort of line here. But before you get into this area, when you're in here, we have this rate strengthening component that was surprising. And so the question is, what's causing this rate strengthening behavior at low speeds? Or another way to think of it is, why is the fringe weaker than the underlying ice-free bed at these low speeds? Well, it gets back to the mechanics of how the fringe forms, right? And so if you think of this zone here, a fringe that's forming, if you look at the cartoon on the right, at the top, most of the pore space is filled with ice. And as you move down, that ice saturation, or the amount of ice that's in the pore space, decreases, right? And that's just what this plot is showing. Large ice saturation at the top, and that decreasing as you go down into the till until you get to zero, right, at this lower depth. Now imagine there's liquid water in here, which there is, and it has to move through this volume. If you start to choke up the pore spaces with ice, you make it harder for the water to move through the system. And that changes the water pressure inside of this zone. It actually elevates the water pressure to a higher value than it would be outside of this zone. And so here, that's what we're showing here is this normalized, in this case, effective stress, which is the overburden stress minus water pressure, a low effective stress that then increases until you get down into what is in the saturated till. So even though this zone may not be very big, right, it might only be a couple of centimeters, it turns out to be pretty important for how it's regulating sort of the mechanical interactions of right where the ice sits on the bed. And so you can propose sort of a drag response for this frozen fringe or this icy watery mixture that looks something like this that has a coolant component, but also has a strain rate dependent component that importantly depends on ice saturation, this S right here. And so you can rearrange this and integrate it, and that allows you to solve for what the velocity is throughout the frozen fringe. And when we do that, and we compare it to our results, we get a pretty good fit. And so the black line is what we get when we do this sort of assumption or generate this type of equation and solve it for the parameters that the experiment that had the black dots was ran for. And the gray line is what we get when we do it for the open triangles. And in both cases, it fits pretty well. Now, one thing you can do is you can use that velocity that you solved and you can sub it into this regularized coolant. This is the same equation I showed twice before for both the other parts for this transition velocity. And it does actually a pretty good job fitting the data. And so this black dashed line here is the regularized Coulomb response when you fit it against, when you use that expression for the transition velocity. And the data it's compared against are those triangles. And so when we look at debris sliding over a bed made up of till, what we have found is that you get a regularized Coulomb response, right? And so we've got 3 of these 4 end members so far having this regularized Coulomb response for different processes in each one of these, to be honest. Like they're not all the same processes, but they're all sort of feeding back and producing the same general response. Now, what about when you slide debris-laden ice over bedrock, right? A bed that doesn't deform. Does it do something differently? So again, we have this debris-laden ice and that's sliding over the bed. And as it's doing that, it's having to move around these particles or move around the bed and shift particles within here and do all these other complicated aspects. And so the slip response, the bed material will not deform, like I said. And so just like before, the ice has to get around this obstacle. But in this case, the ice isn't this perfectly clean, very viscous material. It's got all this sediment in it. It's got all this dirt that's probably affecting the rheology of the ice to some degree, but it's also affecting how it interacts with the bed and drags along it and things like that. So does that change the physics in any way from the debris-free example? And so why this is important is that essentially all slip laws that are formulated for ice sliding over hard beds, which is most of them, make one big assumption that's important to simplify the slip law. And that is, if you look at the bed of a glacier, here's this sinusoid here would be the bed, below would be the rocks, is that there's always this very thin layer of water, right? And what that water does is it eliminates any friction between the ice itself and the bed material. And so all the resistance has to come from the ice, either viscously deforming around these bumps or regulating around them if it's able to. and that there's no actual friction between the ice and the bed. But you can imagine if you put big rocks in here, and this water film might be only on the order of a micron or so, or not a micron, but a millimeter. If you put rocks in here that are bigger than a millimeter, they're going to poke through that water layer and start dragging on the bed. And so it's an extra source of drag, just like we saw before. It's unaccounted for in virtually all slip laws because it's hard to deal with. So you have these particles, right? And they're at the bed. And what's happening is they're being pressed in the bed with a certain amount of force. And then as the ice slides, in this case from left to right, they're being dragged along the bed. And the resistance that the particles supply to the glacier moving is directly related to how hard they're pushed into the bed, right? If those things are pushed in the bed really hard, they're going to be very hard to slide along. But if they're just barely touching the bed, they're going to be easy to push along. And so you kind of got to know what's regulating how hard these particles are being shoved into the bed. There's a couple different ideas of what's causing this. Things like that the particle at the bed is largely the contact force, this S of C, what they call it, is related to the difference between the ice pressure and the water pressure at the bed. That it has to do with how fast the ice flows around the particle is another idea. You can imagine as the ice is flowing down towards the bed, say it's melting down here, and the ice is flowing from top to bottom, the ice will have to viscously deform around this particle or regulate around it, and that exerts a drag that puts it into contact with the bed. Another is that there's a thin film of water around it, and that viscosity of the water within that film is helping to regulate the drag. And so this is, again, one of these pre-melt film theories. Why is this important, or where does it become important? Well, imagine we go back to this scenario where we have a bed. In this case, it looks like a stair step, and there's a bunch of debris in the ice. And we have these cavities, right? And so there's only certain parts of the bed, like right here, where there's actually ice that has debris in it that's directly in contact with the bed. But in these areas, the ice has to, in addition, in order for it to move forward, it has to sort of flow around these bumps. And so it's extending, right? It's extending to get around these bumps. And that extension is drawing ice from higher up closer to the bed. And so if you're this particle here and the ice is flowing from high up in the ice or a little bit higher up in the ice towards the bed, that's essentially pressing this particle into the bed. And so areas that undergo lots of extension, you might imagine have lots of force pushing these particles into the bed, and then they could supply more resistance. And so to try to study this, we took, there's actually a three-step approach, but I'm only going to talk about two of them here. We ended up putting this in a big ice sheet model in the end. But for these parts, we used the ring shear to sort of look at what the physics were on the scale that we could control it. And then we implemented those into Elmer ice and used it to solve it for bed conditions that we couldn't replicate within the ring shear because they're too complex and they don't scale, essentially. So again, we use this ring shear device and we put a bed in here, right? And the bed is not flat. That's the important thing, right? It has two flat sections and two steps in it, right? And these steps provide sort of another obstacle that the ice has to flow around as it's moving over the top of this bed in the experiment. And we run two experiments, one without debris. And so we just fill this up with ice and we slide it over, and that gives us some baseline. And then we do a second experiment with debris. And so we put these clasts in the bed. And what we do is we compare the experiment that had no debris to the experiment with debris and see if there's any difference in the drag signature between the two. Because if it is, it's due to those clasts in the bed and whatever drag they're exerting on the system. And so here's the results, right? The x-axis is the slip velocity, and the y-axis is the drag. And the brown line here is the drag we experienced in the experiment with no debris in the ice. And the green is the drag we experienced with debris in the ice. So important one thing is that we get this big increase in the drag, 60% increase, right? Basically equivalent to what Iverson saw at Ingebrigtsen, where a significant portion of the drag is actually coming from the debris. That's interesting. So the debris is, if nothing else, adding sort of a step function increase in the drag. When we separate this two, we look at the difference between those two. We sort of see as the sliding speed goes up, we have this general increase in the difference between the two as they go up. What that's telling us is that there's this rate component to this. As the ice spins faster and faster, the drag is going up higher and higher and higher. And so when we go back and look at these different processes and what's giving rise to the what we observed in these experiments, we kind of can chalk it up to these two different processes: this pre-melt film that's moving around these particles, and some vertical component of the ice as well. And so we have what occurs with the debris-free ice, just like we saw before, this regularized Coulomb response. We have this component that's related to the effective stress and the vertical velocity. And we have this other component or the effective stress, and we have this other component that's related to the vertical velocity. And this one is important, right? It's important in particular because it has a velocity dependence on it, right? It changes the form of the function from something that would be just regularized Coulomb. And so here's the case of the debris-free ice in blue and the debris-laden ice in green. And these dashed lines they're not best fit lines. They're actual predictions that you make from this new parameterization of these processes. So the blue is just basically Schouff's extrapolation of ice over a wavy bed. Does a good job. And then when you add the debris components, the new one, you get this rate strengthening response that we've seen here. But obviously, glacier beds don't look like perfect sinusoids or steps, right? Just like before. And so first, what we want to do is make sure that we can add these new components of frictional resistance into Elmer ice and recapture the types of responses that we were seeing in the ring shear. If we're confident we're doing that, then we can extrapolate this again to more complex 3D bed geometries. Right. So here's the simple step features, cavities, these are the stress and the pressure, sliding velocity on the x-axis, resistance on the y, debris-free ice in purple, and debris-laden ice in blue. And you can see that they start to deviate as the sliding speed goes up and up and up, just like we saw in the experiments. And so we're fairly confident that we've got these processes parameterized relatively well in this Elmer ice model. But like I said, the beds of real glaciers look like this, not like little steps like we have in their sinusoids. And so how do we extrapolate it to something like would be more realistic? Does it change the form of the function drastically like we saw, for example, with the debris-free ice where we had the double valued sliding law in a very simplified bed to something that looks more like this? Well, we go back to these four fields in Switzerland and Canada, and we slide the ice over it. But this time we put the new estimates of how the drag is being supplied by the debris in there. Look at how it changes the form of the slip law. So if we look at this one, Castle Guard, here's the vertical ice velocity, which is one important particle, or one important piece of the parameterization that is needed in the system. And so we put it in there. And this is the result, right? And so this is Castle Guard Glacier. X is the sliding velocity. This is what Hellenau got for a debris-free bed. Really typical regularized Coulomb. This is what we get when we add debris bed friction, right? It keeps going up and up and up. There's this rate strengthening component that as the ice slides faster, the bed provides more and more resistance. So debris friction slip law is distinct from the clean ice when we add the debris in. And so when we look at all four of these different four fields, like maybe that was just something that happened to the Castle Guard and it wasn't the case for the other ones that have different lithologies and bedrock types. We find actually the same thing in all of them, right? Again, purple is the clean ice in all of these, and the blue is the debris-laden ice. And in all instances, we have this rate strengthening response that deviates from the clean ice. So when we have debris-laden ice slipping atop a hard bed, we have something different, right? We have a rate strengthening component. This is very helpful because it provides something to continually provide stability to push back on, if the driving stress, for example, was going up, this would be a place or places of the bed that have these conditions, a hard bed with debris in it, would be an area where you could continually supply more resistive stress to balance out increases in the driving stress. Why does this matter, right? Well, I've been talking about this and showing these things all in this way, right? The sliding velocities on the x-axis, the thing's going faster and faster, and the y-axis is like the bed's ability to resist. But when you actually model these things, what you're putting in is the stress conditions, right? You're building up the geometry of the glacier and giving it some sort of stress, and that gives you some prediction of how fast the glacier will move. So imagine this x-axis here is stress, right? The driving stress. And in this case, where it's the debris or the clean ice, a small change in the driving stress will result in a huge difference in the sliding velocity, right? It means that you got to have everything exactly right to get the right answer here because this thing is so sensitive once you get into this flat portion. Conversely, if you have this new component, this debris-laden ice component, as you push harder and harder and harder, you only get little changes or incremental changes in the resistance or in the sliding speed of the beds, little increases in it. So it's a much more stable system, and it makes it easier to sort of model in general. So the debris-laden hard bed slip law, a couple of the takes is that the bed normal ice velocity increases as the sliding speed goes up. That makes sense. As those cavities get bigger, it's concentrating the stress on smaller and smaller areas. That ice has to flow around what's left of the bed in those parts, and that pushes those particles into the bed harder and harder and harder. The debris causes a rate-dependent strengthening. Um, and that's what I just showed there before. And this, to me, is an interesting aspect of it is it really helps to numerically stabilize ice sheet models, right? If you have a part of the bed that can have this rate strengthening component to it, and is not so much the regularized coolant, those are the really important parts of the bed, right? So the overall implications, these different models give, or these all different slip laws give modelers a physically based slip laws that can be used that, aren't sort of there's actual physical processes in there that are giving rise to their forms and functions, and we can make specific predictions about where they'd work and how they'll work and things like that. That debris laden ice slip on top of hard bed is important because it provides a rate strengthening mechanism that helps stabilize the models. That's not there when you don't have the debris. And interestingly, it's not there when you do have debris, but the bed is soft, right? When the bed's deforming. It actually pushes it closer to Coulomb in that condition. But what this means is knowing the spatial distribution of hard versus soft beds is particularly important, right? Because there's going to be some parts of the bed in this world that can do a lot more work to stabilizing the glacier than other parts of the bed. And in knowing where those are, with either using seismics or radar or whatever, is going to be important to getting the model predictions correct overall. So I'd like to thank This Works All, it's funded by NSF. Here's some of my group. This Jeremy Brooks is the guy who did the last part here. So I will stop there and I'm happy to take any questions. Thanks.
Amazing, Luke. That was excellent. Thank you very, very much.
Mhm.
I'd like to, wow, look at all the applause roll. I'd like to open it up to any questions. We've got one from Georgia here to kick us off. Georgia, do you want to unmute and ask your question, or would you rather I pass it along?
Um, Sorry, can you hear me? I'm in a cafe, so
Yeah, works good.
okay, perfect. Super awesome presentation and go Badgers. My question is like on what sort of timescales would we be seeing like a glacier be in this rate strengthening mode and Coulomb mode? Like would some really be one or the other, or would they vary on like seasonal timescales?
They could, if it depends on where they are, sort of relative to that transition speed. So, like for example, if they slowed down enough in the winter, they could transition into the rate strengthening regime, or if they sped up in the summer. I think probably on the more likely scenarios that they're not changing a lot temporally, but probably changing spatially. So, like some parts of the bed are behaving largely in one way, and other parts of the bed are behaving another way, and those could change over long time scales or medium time scales. You can imagine if some part of the bed had a bunch of till on it, and then all that till was evected away and you made it down to the bedrock, then you could change from one type of process to the other.
Mhm.
But that depends on A, how fast you can evect the till, and B, how much till there was there to start with.
That makes sense. And I do have one more quick question. The experimental setup looked super, super cool. And this is maybe a silly question, but I was just thinking like if you put colored beads instead of white beads, then you'd be able to see maybe more in a video. You could even like do picking or movement tracking or something.
Yeah, that's a good point. Those bees are all we well, we use those because Alan Rumpel wanted me to. Let's put it that way. He's on here, so I'm gonna say that. But it's so we could simplify the bed to a way that made it very easy to compare against the theory. And the reason that we use those beads is because they're what's called monodispersed, and so they're almost perfectly spherical, and they have a really narrow grain size, but they're not a natural. They're glass, right? They're blowing them in some factory or something like that, and so. We'd have to dye them, which we probably could.
Mm,
I don't know how you dye glass, but there's probably a way to do it. And yeah, you could track them that way.
super cool. Thanks so much.
Yep.
Thanks, Georgia. Anyone else?
I'll jump in. I typed my question hastily just to keep it moving. Um, so for the fourth case, the um, debris-laden ice on a hard bed, are we just too zoomed in? Is it possible that curve is going to turn over if we can move the ice fast enough? Or is it fundamentally, are you certain it's fundamentally different physics?
That's a good question. It should hold as you move faster, assuming there are always bigger bumps, right? So, like if we've looked at a certain size scale in these models, which is well, to run the Elmer Ice model on the scale was hard because we had to three-dimensionally resolve the cavities and all those things, which meant we were limited in the domain. And so the domain is by itself limited to sort of 20 meters in this case. But say we had much bigger computers and we could do domains that were 10 times bigger. I still think you would see that pattern because then you would have but bigger bumps that still are able to hold the stress back. Yep.
Michael.
Now, since we just said the word bump a lot, I'm just curious. Wait, so because I now I'm sorry for the subglacial theorist. I can't remember what it's, but the bump sizes, right? Have you tested specific bump sizes and see like what ice thicknesses impact sliding depending on like like I don't know if is it a big bump if it's like one ice thickness in space or something like that, Luke?
Uh, Sort of. We've done different roughnesses. We've done two right now, I would say. But right at this exact moment in the ring shear is a bed that is designed to look at that process. And so we've explicitly made a sinusoidal bed that has two different bump geometries. The wavelengths are the same, but the amplitudes are different to look specifically at this effect you're talking about. And what we're interested in is not only that, but the cavity geometry. I think there's some problems with the way the geometry of cavities is like parameterized in models a lot of the times. And so we're using different bump sizes to look at that process. But well, in that case, well, this will be the first instance where we've done it. Yeah.
Awesome. I have one other quick follow-on question. The very, very specific technical. I was just curious. It was one of in I think Dougal Hansen's paper he figures you showed, and one of them was like I think it was the experiment when you had without class and with class, but there was only one point where it was like at 200, I think, meters per year velocity, but the other one was missing. Is there a reason why you didn't go up faster for the without class case?
Yeah, I should put there's way more data points in that range. I just
Okay.
that second plot I showed, all of those data points, there's like 13 of them are on that line.
Mm,
I just didn't so you can think of it as one of those data points has like 10 actual data points
mm.
within it, right? Yeah.
Okay.
Yeah.
Awesome. Cool. Thank you.
Interesting. Anyone else? As a non-glaciologist, I'll just say that ring shear piece of equipment looks really, really cool.
Yeah. Yeah, it is. There's well, Well, right now there's just this one operating here, and then the Iowa State one has gone to Dougal Hansen at Wash U. So, and then we're building another one here. So, right, there'll be a couple ring shears if people are interested in doing ring shear experiments. They should let me know.
Yeah.
I could
We're at the
jump
top
in
of,
with,
oh,
oh,
yeah, Amy.
sorry, if there's time, I'll jump in with
Yeah.
one more question. Great talk. And yeah, this is great for understanding how the ice responds to conditions at the bed. And I'm wondering if you have ideas for how this might change how conditions at the bed respond to ice flow. So like how do the cavities form with different velocities? And I'm wondering if we should be changing how we parameterize the opening of cavities. And if your experiments could give us ideas about how to better do that.
Yeah, so the one way to think about it is the additional drag that's provided by the debris should, for the same driving stress, slow the glacier down, which would ultimately result in the cavity being a different geometry than it would have been with no debris because the ice would have probably been moving a little faster. So there's that aspect of it. And then the experiment just specifically to look at the cavity geometry. Yeah, we can use this device, and that's like literally what we're doing actually right now. We've come up with a way to map the three-dimensional geometry of the cavity during the experiment through the wall, and then systematically change the sliding speed and the effective stress to watch how the cavity geometry evolves. And look at, for example, in these subglacial hydrology models like GLADS and Shakti, the opening and closing terms on the cavities to see if like they're appropriate or not appropriate, or if we need to rethink how they're implemented in those types of parameterizations.